Hello everyone, welcome back to my video. So basically this is the third chapters of the Strength of Material 1 course. Okay, in the first chapter we have analyzed the stress and strain in the material when subjected to axial load. Then in chapter 2, I hope you still remember, we look on how the material behave under torsional load. Now in this video I will talk about the material behavior under pure bending. So before we start our lecture, let's see what are the topics that you will learn in this chapter. So basically there are 6 videos that I have prepared which cover all the topics under pure bending. So video 1 basically is to explain how the material will behave under pure bending. Also the analysis of stress and strain or deformation of the beam made from homogeneous material will be presented. So what is meant by homogeneous material? Homogeneous material means single material or the same material. Okay. And then some example and step-by-step procedure, step-by-step analysis to solve the problem involving pure bending will be given in the following videos of part 2. In video of part 3, we will cover the analysis of stress and strain of the beam made from composite material. Okay, what is meant by composite material? Composite material means 2 or more material. So we will analyze the beam that made from 2 or more material, okay, or composite material. And then the concept that is explained in video 1, okay, will be applied in video 3. Okay. Following video 3 is video 4, where I will show you how to solve the problem involving composite material. Okay, I will show you step by step. I hope this will prepare you with a basic idea or concept before you will facing the real problem in the future. The next topic is analysis of reinforced concrete beam under pure bending. So in this topic, we will see how the steel is being used to resist the tensile stress in concrete. So this topic will be covered in video part 5. Okay, next is video part 6. Okay, in this video I will show you some sample of problem and step-by-step solution to the problem, so that you will get some ideas, okay, how to solve the problem that involving reinforced concrete beam. Okay, so let's start with the definition of pure bending. So what is the pure bending? By definition, when a member is subjected to equal and opposite couples or moments that acting in the same longitudinal plane with the absence of shear force. Okay, so means that the shear force is equal to 0. Okay, so only so the member is only subjected to couples, okay, or moment, then the member is said under pure bending. Okay. But bear in your mind that in most real problem cases, okay, in most real problem cases, the beam is usually subjected to both shear and also couple force. Okay, but this chapter actually is aimed to prepare the student with the basic concept of analysis of beam before more complex structure where the shear force is involved can be solved. Okay, so let's look at in picture 1, okay, which is here. So what you can see here is one man, okay, lifting the barbell. Okay, so this is what we call as barbell. Okay, and then the free body diagram of barbell is shown in picture 2. Okay, if we analyze the barbell, we found that the shear force at portion CB, which is here, okay, the shear force is equal to 0. Okay, shear force V equal to 0. Okay, okay, so we can see from this diagram. Okay, so this is the shear force diagram. So for portion CD, the shear force is equal to 0. Okay, and then for portion AC, okay, for portion AC, there are some value of shear force, and same here for portion DB. So the shear force also have some value, so means that the shear force is not equal to 0. Okay, also for portion AC. Okay, so here, okay, don't worry if you don't know how to draw the shear force diagram, because the way how to draw the shear force diagram will be discussed in the next chapter. Okay, so don't worry. Okay, what I try to show you here is for this case of barbell, okay, the portion CD, the shear force in portion CD is equal to 0, and CD is only subjected to couple moments M, okay, M and also M prime. Okay, so for this case, we call that we can say that the CD is under pure bending. Okay, pure bending. So if you look on the definition of pure bending, okay, the member is subjected to equal and opposite couple moment. So for this case, is the M and also M prime, and the shear force is equal to 0. Okay, so for CD, so the V is equal to 0. So CD is under pure bending. Okay, now let's do some revision on what type of forces that induce the normal and also shear stress. Okay, so this is the picture that I have shown to you in our previous physical class before MCO, okay, before movement control order. So I hope all of you still remember this diagram. Okay, this diagram. What we can see from the diagram is the stress as well as the strain can be divided into two types. Okay, the first one is the normal stress strain, and then the second one is the shear stress strain. Okay, clearly in this diagram, the normal shear stress and strain will be developed in the structure when subjected to axial force. Okay, so if the structure, okay, so it means that if the structure, for example here, is subjected to shear force, okay, sorry, axial force, okay, is subjected to axial force, then the normal stress and strain will be developed in the material, in the structure. Okay, and then the normal stress and strain also will be developed due to the bending moment. Okay, due to bending moment. And then the second type is shear stress and shear strain. Okay, so shear stress and shear strain is developed in the material due to the transverse force and also due to the torsion. Okay, so means that if we have the structure that subjected to transverse force and also torsion, then we know that the stress that developed in the structure is shear stress, okay, and also shear strain. All right, so as this video is all about the bending, okay, all about the bending, so you should expect that the stress and strain that will be developed in the structure is normal stress and strain. Okay, so we are talking about, in this chapter we are talking about the pure bending. So we will expect that the stress, the type of stress that will be developed in the structure is the normal stress. Okay, same thing for strain, normal strain. Alright, so now let's we look at the deformation of beam under pure bending. Okay, as shown in picture 4. Okay, we can see there is the beam, okay, and before deformation. So this is before deformation, and the other one is the after deformation. So this is after deformation. Okay, after deformation. So what we can see from this figure is the after deformation, okay, due to bending, okay, due to bending M, okay, or moment M, okay, due to moment M. So what happened is the beam will bend uniformly, okay, uniformly, okay, to form a circular arc. Okay. Now let's imagine that the beam in picture 5, okay, which is here, this beam. Okay, we imagine the beam in picture 5 is discretized into the small square element. So I discretize that beam into the small element, okay, into small element, square element, so that we can analyze in detail what happened to the every point, okay, every point of the beam after deformation. Alright, as I mentioned previously, under pure bending, the beam will bend uniformly. Okay, so this is clearly shown by the red horizontal line in picture 6. Okay, we can see here, okay, let's say we take out one line here, okay, horizontal line, okay, and then this is before deformation, and then the other one is after deformation. This is after deformation. Okay, sorry for my writing, it's not good. Okay, so let's say this is a before deformation, okay, and then the same line after deformation. Okay, let's say the before deformation represented by the line, this line, and then after deformation represented by this line. So we can see here the line before deformation will bend, okay, will bend nicely, okay, to form circular arc after subjected to bending moment M, okay, bending moment M. And then also what we can observe from the beam is the vertical plane, okay, vertical line, the vertical plane. So here, this vertical plane. So after deformation, this plane will rotate with certain angle. Okay, let's say this plane represented by this one, and then after deformation represented by this one. So what you can see from here, okay, after deformation, the vertical plane of the beam will rotate with certain angle theta, okay, but the surface remain planar or remain flat, okay, remain flat. So this behavior basically, basically give us some idea on how the stress distribution in the beam will be. Okay, so this gives us what I mean is it will give us some ideas, okay, how the stress and also strain distribution in the beam will look like. Okay, so later in the next slide we will see that the normal stress and also strain distribution is varies linearly, okay, which is consistent to what we observe here. Okay, we can see later how the stress and also the strain distribution. Okay, so for information, the stress and also the strain distribution will consistent that what we observe in this slide. Alright, so now let's look at the beam after deformation. Okay, here, which is this one. Okay, what we can see from here. Okay, so we can observe that the total length of the top surface becomes shorter. So this is the top length, the length of top surface. The length of top surface before deformation, and here is the total length of top surface after deformation. So we can see here what happened is the L for top surface after deformation is less than the length for the top surface before deformation. Okay, before deformation. So, and then if you look at on the bottom surface, okay, if you look at on the bottom surface of the beam, so the L, the length for the bottom surface, okay, before deformation. Let me write after first, after deformation first. So the length of bottom surface after deformation is greater, okay, is longer than the total length for the bottom surface before deformation. What does it mean? So it means that the top surface will be in compression. Okay, because the length becomes shorter. Okay, and then for the bottom surface, so basically the beam is under tension. Okay, why? Because the total length increase, okay, after deformation. So we can, from this observation, we can conclude that when the beam is subjected to bending moment or couples, so one side of the beam will be in tension and the other side will be in compression. So when we design the beam in future, for example, so we have to ensure that the material that we choose should be able to resist both tensile and also compression stress. Okay, now let's further analyze the beam. So from the analysis, we know that the length of the top surface of the beam decrease after deformation. However, the total length of bottom surface after deformation is increased. Okay, so that behavior can be shown in picture 7. Okay, picture 7. So it means that the top part is negative. Okay, the deformation is negative because the total length decrease. Okay, so the deformation basically equal to L after minus L before. Okay, before deformation. So this is equal to the deformation. So the deformation is negative at the top surface and the deformation is positive at the bottom surface. Okay, so from this so as we can see from this picture, so we know that there is a changes between negative deformation to the positive deformation. Okay, at the top surface of the beam to the bottom surface of the beam. So from this diagram we can say that, okay, I can say that they must have a plane, okay, or the surface where the length is constant. Okay, the length is constant means the length after should be equal to the length before deformation. Okay, because one side we have negative deformation, the other side we have positive deformation. So I can conclude that they must have the plane where the deformation is equal to 0. Okay, equal to 0. So which is this point. In this case is if we look at this figure, this point. Okay, this point basically is the deformation equal to 0. So that plane, okay, that's plane we call it as a neutral plane. Okay, we call it as a neutral plane. Okay, or neutral axis. Okay, so by definition, neutral plane or neutral axis is the plane or the axis that has zero deformation. Alright, and note that this neutral axis or neutral plane is passed through the centroid, okay, of the cross-sectional area of the beam. Alright, so in summary, we can say that the beam with plane of symmetry that subjected the beam with plane of symmetry in pure bending. Okay, so for the case of this type of beam, the beam after deformation, the beam will remain symmetric. Okay, will remain symmetric, and then the beam will bend uniformly to form a circular arc. Okay, and then also the cross-sectional plane pass through arc center and remain planar. Okay, so the cross-sectional plane, okay, which is here, the cross-sectional plane, okay, basically will pass through the arc center. So this is the arc center. Okay, so all this plane basically will pass through the arc center. Okay, something like that. Okay, alright, and then the length of top surface will decrease and the length of bottom surface will increase. Okay, as shown in picture 8. Okay, so that is the top surface and that is the bottom surface. Okay, and then the neutral surface or neutral axis must exist that is parallel to the upper and lower surface and for which the length does not change. Okay, this is what I already explained in the previous slide. Okay, in the previous slide. And then stress and strain are negative for the case of compressive stress at one side. Okay, one side, and positive, which is tension, is in tension on the other side. Okay. Okay, now let's look at how the strain, okay, the normal strain, which is the strain at x direction, is derived from the beam that deform under pure bending. Okay. Okay, let me choose the pen first. Okay, all right. So picture 9 shows the beam after deformation. Okay, so this is the beam after deformation. So the length at the point just above, okay, just above the neutral axis. Okay, let's say the solid line here is the neutral axis, and then the dashed line here is the somewhere above the neutral axis. Okay, and then the length represented by L prime. Okay, so the length of the beam at neutral axis represented by L. Okay, so we can write that the L prime is equal to rho minus y times theta. Okay, so how we get this equation? So based on the rule of circle, okay, rule of circle, let's say we have, let's say here represent by S, and let's say this is R, and here is theta. Okay, so based on the rule of circle, the S is equal to R theta. Okay, so same thing here. So for L prime, okay, L prime, which is, if we compare to this diagram, is equal to S. Okay, so L prime is equal to P minus Y, okay, which is from here to here. Okay, from here to here, that is the P minus Y. So similar to here, S equal to R theta, so that is the R. Okay, so for this case, the R equal to P minus Y, and then divide, multiply by theta. Okay, multiply by the angle here. So we get L prime equal to rho minus Y multiplied by theta. Okay, and then the L. Okay, the L, the equation for the L, the length L, okay, we can write is equal to rho times theta. Okay, because here is the L and here is the rho. Okay, so similarly, L equal to rho theta. Okay, so we know that the deformation is equal to L prime minus L. Okay, L prime minus L, so which is equal to so if we, okay, so Y deformation equal to L over L prime minus L. Okay, so if we make it the L prime into straight line, okay, so let's we put the L, okay, convert L into the straight line. So let's say this is the L prime, and then the L here also we put in straight line L. Okay, so the deformation basically is, because we know that at the neutral axis, so that is the neutral axis, the length is constant before and after deformation. So that's why we say that the deformation is equal to the final length minus the L, because the L is constant, okay, before and after deformation. Okay, and then we substitute the value of rho, the value of L prime, okay, which is equal to rho minus Y divided times theta. Okay, so that is the L prime, and then minus L, so L is the rho theta, and then we get the deformation equal to minus Y theta. Okay, Y is theta. So what is the Y? Y is the distance of arbitrary line, okay, any line of in the beam with respect to the neutral axis. Okay, so that is Y. Okay, that is Y. So as we know, the epsilon s, which is the strain s, is equal to the deformation over the original length. So we can replace the value of deformation equal to minus Y theta. Okay, and then divided by L, L equal to rho theta. Rho theta, yes. Okay, so we cancel out the theta, so we get epsilon x equal to minus Y over rho. Okay, so for the maximum strain, okay, for the maximum strain, we can replace the Y by the value of C. Okay, by the value of C, because the C is the longest distance. Okay, the longest distance of the beam from the neutral axis. Okay, so we can replace Y equal to C, and then we get the epsilon m. Okay, epsilon m is maximum strain. Okay, or we can rearrange, okay, in terms of rho. So rho equal to C divided by epsilon m. Okay, so therefore, okay, if we compare between, okay, epsilon x equal to minus y over rho and epsilon m equal to equal to c over rho, okay, c over rho, then we can combine these two equations. Okay, we can combine these two equations and then becomes this one. Okay, this is easy to convert. This is easy to show the epsilon x is equal to minus y over c sigma m. So from here, this is basically is the linear relation between epsilon x and also epsilon maximum, which is a strain x and also a strain maximum. So as I said again, this is the linear relation. So if we draw the stress, the strain distribution, okay, the distribution of the beam, we can see the strain is linearly, okay, varies linearly from 0 at the neutral axis, okay, neutral axis 0, which is y equal to 0, okay, y equal to 0, so the strain equal to 0, okay, and then varies linearly to the up to the top surface and also bottom surface. Okay, now we proceed with the stress, normal stress due to bending. Okay, so how to derive the stress, okay, developed due to bending. All right, as we know, for linear elastic material, Hooke's law applies, okay, when the material is homogeneous. So the Hooke's law is given by sigma x is equal to E epsilon x. Okay, epsilon x. Okay, so if we replace the value of epsilon x that has been derived in the previous slide, so we can write that sigma x is equal to E, okay, so epsilon x is minus y over c sigma epsilon m, okay, and then we can rearrange become this equation. All right, so because the stress also varies linearly, so we can write the sigma x is also equal to minus y over c sigma m, okay, sigma m, because why? Because E sigma m basically is equal to E epsilon m, E epsilon m is equal to sigma m. Okay, so this is equation for sigma m. And then for static equilibrium, we can see from this figure the total force, the total axial force, okay, is equal to 0. Okay, so that is the force in x direction, okay, negative x direction, and then this is the force x in positive direction. So the total must be equal to 0, okay, for static equilibrium. So we can write that the summation of fx must be equal to 0. So summation of fx equal to the integration of sigma, okay, so this is the integration, so this is basically the fx equal to the integration of sigma x dA. Okay, so that is based on the equation of stress equal to F over A. Okay, so F equal to, from here, F equal to sigma A. So that is the sigma A. Okay, and then we can substitute the sigma x by y over c sigma m, okay, which is here. Okay, sorry, this is a sigma x. So sigma x equal to minus y over c sigma m. So we substitute here. Okay. Finally, we get that the minus sigma m over c, okay, integration of y dA is equal to 0. Okay. So here, because the force directed to the left and then this force is directed to the right, so what happens, it will create a moment, okay, moment m. Okay, so let's say this is the z-axis, okay, this is the x, this is y, and this is the z. So this moment basically is acting about y-axis, okay, this moment acting about y-axis, so we put z-axis. So sorry, this moment acting at z-axis, so we can write as a mz. Okay, so the total moment, okay, for static equilibrium, the total moment is equal to mz. Okay, mz. So we can write mz is equal to the integration of y sigma dA. Okay, y sigma dA. Okay, so sigma dA actually is the force and y is the distance. Okay, is the distance. Okay, so because the moment is equal to fd. Okay, d is the distance, f is force. So for this case, force is the sigma x dA and distance is y. Okay, distance is y. So we substitute the value of sigma x. Okay, we substitute the value of sigma x here. Okay, so the equation become minus y multiplied by minus y over c sigma m. Alright. Now, because the sigma m over c is constant, okay, this is the constant. Okay, sigma m and also c is constant, so we can put it outside here, and then the moment z, okay, about z-axis equal to sigma m over c, okay, integration of y square dA. Okay, so y square dA, this is the equation for moment of inertia. Okay, I hope you still remember, this is the moment of inertia, y square dA. So it's become, and then we can write the equation for moment equal to sigma m I over c. Okay, alright, so we know that the m is equal to sigma m I over c, so sigma m is equal to mc over I. Okay, mc over I. Or we can write in terms of y, okay, in terms of distance from the neutral axis. So sigma x, okay, we can write the sigma x basically is equal to the minus my over I. Okay, so this is what we call as a flexural or bending stress formula. Okay. Alright, the other important parameter is curvature. Okay, so the deformation in the transverse cross section of the beam can be quantified by the curvature or radius of curvature. Okay, so what is the curvature? Curvature is given by 1 over rho. Okay, 1 over rho, where this is what we call as a curvature. Curvature. Okay, so what is the rho? Rho is called as radius of curvature. Okay, so you can see by definition the rho is measured from the center of the arc okay, from here, center of the arc, to the neutral surface. Okay, so that is the rho. Okay, measure from the center of arc to the neutral surface. So that is the neutral surface. Okay, so I don't think I should show you how we derive this equation. Okay, so the same formula we are using the same formula what we have derived previously. So we can show that the 1 over rho is equal to the m over ei. Okay, so this is what we call as a curvature equation, and as I said, 1 over rho is the curvature, and rho itself we call it as a radius of curvature. Okay, now let's look back at the fractal or bending stress equation that we previously derived, where the stress sigma, okay, the stress sigma is equal to mc over I, okay, or sigma x equal to my over I. Okay, if we calculate the sigma maximum, which is sigma m, so equal to mc over I. So this is what is shown here. Okay, so this relationship show that the value of bending stress is influenced by the moment of inertia, okay, moment of inertia I, and also c, okay, where c is the distance from neutral axis to the lower or upper surface of the beam. Okay, so let's say we have, for example, we have a rectangular beam like this, and then let's say this is the neutral axis. Okay, here will be the c, okay, the distance from neutral axis to the top surface or bottom surface, okay, or here, okay, here c. Okay, in other words, the stress will increase as the c is increased, but the stress will decrease when the I is decreased. Okay, so since the bending stress sigma m is influenced by two parameters, which is a c and I, it is better to rearrange the equation, become sigma m equal to m over s, where s is equal to I over c. Okay, and the I over c, sorry, this is I over c. So I over c here is called section modulus. Okay, section modulus. Alright, so in this form, okay, if you look at here in this form, sigma, which is a sigma m equal to m over s, okay, in this form, we will see that the bending stress sigma m is inversely proportional to the s, okay, where s is, as I said, is defined as a modulus, elastic section modulus. Okay, so clearly from here, the beam should be designed with large value of s. Okay, we have to design the beam that has higher value of s, so that the beam will provide better resistance to the bending. Okay, so what happens is we use the beam with higher s, so the sigma m will be lower. Okay, we will lower. So that is good, because the stress because in design we have to make sure that the stress is always low. Okay, it's always low in value. Alright, so let's consider the picture 13. Okay, the section modulo S is equal to I divided by C. Okay, so if we consider this beam, okay, we know that the S is equal to I over C, and then if we substitute the value of I, okay, so the I is basically equal to 1 over 12 BH power 3, and then we substitute the value of C equal to H over 2, okay, from here. So this is the H, so C equal to H over 2, okay, over 2, and then finally we obtain the S is equal to 1 over 6 A times H, okay, times H. Okay, and then since both rectangular beam, okay, you can see here rectangular has equal cross-sectional area. So the cross-sectional area for the first beam and the second beam is the same, okay, 15 times 10 power of 3, okay, so means that the A are the same, okay, the same, so that we can say that the beam with higher depth or height will result higher section modulus, okay. So from here the cross-section area is the same, okay, so which beam has section modulus, higher section modulus, we can say that beam 2, okay, beam 2 will have higher section modulus because the H is higher, okay, the H is higher, okay. Also so because the S is higher, then the stress subjected to the second beam, okay, will be lower, okay, compared to the beam in beam 1. Okay, now let's look at picture 14 and picture 15. Okay, so picture 14 and 15 show two similar beams putting at a different orientation. Okay, so note that the beam in this picture both has the same cross-section area of 50 times 10. Okay, so we have a two beam, okay, beam 14 and also beam 15, and then both beam has the same cross-section area, okay, okay, which is the A is equal to 50 times 10, okay, similar to here, okay, the cross-section area of beam 15 is equal to 50 times 10, okay, so the area is are the same. Now let me ask you one question. As a future engineer, which orientation, this one or this one, will be chosen to minimize the internal stress developed in the material? Okay, so let's say the beam is subjected to the same magnitude of M. Okay, let's say this is M1, and also beam 15 also is subjected to the M1. Okay, the same magnitude of bending moment. Okay, so the question is which orientation you should choose so that you can minimize the internal bending stress developed in the material. Okay, so which one? So I leave it this question to you. Please think about that. Okay, so let's move to next slide. Okay, all right, so as I said, as we discussed before, the bending stress sigma m is equal to the mc over I. So this table basically provide the equation for I. Okay, so for the simple shape, for example, rectangular shape, okay, triangle, circle, semicircle, and other simple shape, so the value of I can be found in many literature or reference book. So you can find out the moment of inertia for this shape in many resources. Okay, so there is another simple shape. Okay, where the I can be directly calculated using the given equation. Okay, so depending on which axis the beam is subjected to moment. Okay, and then the last but not least is the properties of American standard shape of beam. Okay, for various standard shape of beam, the properties such as the area, depth, moment of inertia. Okay, that is the moment of inertia. Okay, with respect to the x-axis, so means that here, and then with respect to y-axis, so means it's the moment acting in y-axis. Okay, and section modular S. Okay, this is the section modular S, which is S equal to I over C. Okay, you can find all these properties in many reference books, standard and other resources. Okay, and then this is example of the value for different designation of beam. Okay, beam. So I took this table from reference book. Okay, so for each dimension of the beam, okay, it has been designed different type of beam has different designation, so that you can select which beam is the most suitable to be used depending on several design requirement. Okay, so there is another different designation of the beam, also same here. Okay, now the last but not least is the fracture surface of the structure. Okay, for this case is the wood specimen that fail in bending. So clearly from here, okay, you can see that the tensile stress below the neutral axis, okay, the tensile stress, so for this case, okay, the below the neutral axis is in tension, and the above the neutral axis is compression. Okay, so compression, negative and positive. Okay, so that is the neutral axis. Okay, so clearly that the tensile stress below the neutral axis will cause okay, again we can see from here the tensile stress below the neutral axis, okay, will cause the wood to pull out. Okay, they pull out, and then the compressive stress, okay, at the part above the neutral axis will pull in the wood. Okay, pull in the wood. Then the fracture surface will look like this. Okay, it looks like this. Okay, so this is the one of the example how the fracture surface of the material looks like when fail in pure bending. Alright, that's all. So this is the end of video of part 1. Till we meet again in the next video of part 2. Bye bye.